A very good morning to all the participants and the distinguished speaker. I am Reshma Kadam. I, on behalf of SAF CRNTS IIT Bombay, take this opportunity to welcome you all for today's talk on elemental spectroscopy. We have two talks lined up today. The first is ICPAES, which will be presented by Mr. Milind Pathare, and the second one is on ICPMS, which will be presented by Mr. Anthony Thomas. Before we proceed, I will begin with an overview of SAF IIT Bombay. SAF IIT Bombay was inaugurated by our late ex-Prime Minister Shri Morarji Desai in 1976. SAF was established at IIT Bombay with DST support in the year 1976. Center of Research in Nanotechnology and Science, popularly known as CRNTS, was established at IIT Bombay in the year 2006. In the year 2008, both SAF and CRNTS were merged and it came under one umbrella, which is headed by one in charge. Currently, Professor Anil Kotantrial is the head of the department. We have around 16 measure equipment in SAF and 6 measure equipment in CRNTS. SAF IIT Bombay provides measurement services to IIT Bombay students as well as users from various academic institutes, national laboratories and industries. CRNTS also has an academic wing which has more than 65 associated faculty members and more than 80 PhD students. CRNTS, the Department of Science and Technology, DST, has set up sophisticated analytical instrument facility, SAF, in different parts of India. The main objective of setting up this facility is to provide guidance in data acquisition using sophisticated analytical facilities. During financial year 2019-2020, SAF IIT Bombay had more than 2,700 users and we have analyzed more than 25,000 samples. The current slide shows you the facility at SAF IIT Bombay, which are funded by DST. The upcoming dual beam FIB FEG SAF, which is under installation. This slide shows you the facility at SAF CRNTS, which are funded by institute. These are ICPAES and ICPMS facilities which are available at SAF IIT Bombay. Dr. Gajendra Saini is the in charge. To know more details about SAF CRNTS, please visit our website saf.iitb.ac.in. We get samples from all the states of India as well as our neighboring country, Nepal. We encourage visitors from various academic institutes, national laboratories, and industries. You can join us on our LinkedIn page to get the latest update on instruments, webinar, or any event held at SAF IIT Bombay. This is the brochure for ongoing webinar series. All the informations are on our LinkedIn page as well as on our SAF web page. This is the group photo of our SAF staff. We would be very happy to welcome you and help you with your analysis. Now let us move on to the second talk of the day. Let me introduce you to Mr. Anthony Thomas. Mr. Anthony Thomas is the Business Development Director, South Asia and Middle East for Spectroanalytical Instrument, GmbH and NU Instruments Limited. Responsible for ICPMS, TEAMS, GDMS, IRMS, ICPAES, ICPOES and EDXRF. He has been with Spectro over a decade and has over 2 decades hand-on experience in elemental spectroscopy. An important note, I request everyone to post their questions with their name in the question and answer box, which will be answered towards the end of the session. Now, I take this opportunity to request Mr. Anthony Thomas to present his slides to everyone. Over to you, sir.
Thank you, Reshma, for the brief introduction. Thank you, Milind, for the way forward. With this, I start my presentation. This is a session which will cover about inductively coupled plasma mass spectrometer, and my number and my reach out mail ID is there. If something in this presentation is not clear, feel free to reach out to the IIT team as well as to me so we can see best how we can address your concern and meet your requirements. Continuing from where Milind Patari started, this is still about element analysis, but with a difference. Here we start to measure right from lithium mass 6. As you can see from the vertical columns, there are 3 more internal columns. The first talks about the element in its symbol form, the atomic mass unit to the 4th decimal points, and its abundance. Abundance means how much of it is split up in its isotope form. For example, if one look at monoisotope like arsenic 75, at mass 75, its actual atomic mass unit is 74.921594, and it's present as a single isotope, so it's full 100%. Or if you take a biisotope like bromine, which has a mass at 79 and 81, if you add them up in the abundance values, it adds to 100%. Having knowing these are the basic fundamentals, and the source being plasma, which was explained by Milind Patari. It analyzes the elements right from lithium mass 6, and goes down to uranium 238. So this is the mass measuring range of a normal stable ICPMS. The breakup comes up here. On the left hand side, we see the ICP-OES components, the sample introduction system with a channel for the peristaltic pump, the gas flow controller either in volume or mass flow for the gas, and the atomization source being plasma. Here it matches accordingly, similar to what the ICPMS also offers, but from there down the optics changes, because in ICPMS the optic is no more consisting of mirrors or reflectors or gratings. Here you have metal plates, electric field, shields. Resolving parts are in form of ion mirrors or quadruple rods or pre-filters. The basic function is to attract or repel the ions which are created in the plasma. In ICP-OES, you have the detectors which function as a source to convert the light energy, the emission of the wavelength it receives, into electrical signals. Whereas in ICP-MS, it physically counts the ions which are registered on its surface. So here you are mostly addressing trace and trace analysis. Few of the terminology which are associated with ICP-MS. As by now we understand it's all about mass study. So a mass consists of protons and neutrons. Now, when an ionization happens, there are 3 subspecies that gets picked up here: the isotope, isotone, and isobar. When you speak about the isotone, which means the neutrons are same, but the mass number is different. For example, boron at mass 12 and carbon at mass 13. They're different mass number, but they have the similar neutrons. Or if you take the next series of examples like sulfur at 36, chlorine at 37, argon at 38, potassium at 39, and calcium at 40, have different mass numbers, as you can see from their mass numbers which is mentioned on each of these symbols. They have the same number of neutrons in each of them. But if you look at an isotope, the nucleoid is same, but they have the different mass number. The isobar have the same mass number, but different neutrons. Just to tell you, iso means equal, bar means weight. So this is the basic fundamentals of the different mass and the iso series that is generated from the plasma ionization. How do we differentiate them? If a nickel sample or nickel atom is ionized, it throws up 5 possible stable isotopes at 58, 60, 61, 62, and 64. If you look at the natural abundance, that's how they are present at 68.1, 26.2, 1.14, 3.63, and 0.1, 0.93. If the instrument is able to quantify even the mass at 64, it can back calculate or reverse calculate what is the concentration of nickel present at mass 58. So in a way, the total sum of the nickel present in the sample can be quantified. So if you look at the values of protons, electrons, and neutrons, which form the part of the isotopes, it is the varying value of neutrons which defines the isotopes. The atomic number still remains the same, but the atomic mass changes. So this is how the isotope works out. And the atomic weight with which it's defined is 58.69. This, if you compare with a normal emission wavelength, a nickel taken at 10 ppm, you will see it throws up more than 30 odd wavelength lines. So compared to that, measuring an isotope of a given element is much more easier. It's much less. You have something around 200 odd isotopes present. They are stable, they are measured, and you can pick each of them to calculate the total quantity of the given element present in the sample. But there are challenges. This is a table of the polyatomic interferences in ICP-MS. The first vertical talks about the isotopes at different mass number, its abundance present. The third vertical talks about the interferences. So let us take the most frequently measured element, arsenic, which is a monoisotope. Being monoisotope, 100% abundance, it gets interferences from argochloride, that is 40 of mass of argon and 35 mass of chlorine. Argon comes from the plasma. Its chlorine can come from the acid. So you have different kind of combination, or cobalt or oxygen. They all combine together and mimic close to the mass of the monoisotope of arsenic. So let us take an example of arsenic 75, which actually should be 74.921594. So if you look at argon chloride, we also can assume it is at 75, but it is not so. If you add up argon chloride, there is a difference of 0.009642. So the instrument should have a third decimal resolution to differentiate an arsenic from its nearby interferences coming from argochloride. So how does the ICPMS works and offer to meet this kind of requirement? Few more things to understand before we go into ICPMS. The ICP-OES addresses almost around 73 odd elements, whereas the MS talks little about 75. Of course, you are going to physically capture the ions, the isotopes, and measure them. So your detection limits are all in PPT because the detector cannot be saturated beyond a given point. The sample throughputs is you can measure all the elements. It will take around 4 to 5 minutes for each of these element samples, whereas in ICP-OES, you have within a minute's time to capture all the elements and their spectrum if it is a simultaneous polychromator endowed with a Paschen-Runge design. The precision levels are pretty high for ICP-OES vis-a-vis with the range. For ICP-MS, for the given range, it's pretty narrow. The stability are equals the same, but the interferences, even though it looks for few mass ranges, we still have moderate interferences from the matrix. Ionization interferences, that is from the plasma, can also affect, and the mass effects are important over here. Similarly, the interferences from nearby isotopes or coupled isotopes can be a big hindrance, and to resolve them, we need to use different techniques like collision reaction or 90 degrees optics. What is the maximum concentration the instrument can take? 0.1% total dissolved salt content from the solution can be aspirated. Anything beyond than that has to be diluted in the spray chamber with the help of the argon gas. The working cost of this instrument is pretty higher, to a factor of 1.2 to 2 times more than an ICP OES, with the capital cost talking around at 125 to 150K for the basic instrument. Regardless of the make and the model, there are 6 basic components that one is seen in ICPMS. The sample introduction system, consisting of the tubings, spray chamber, nebulizer, torch, the plasma generation system, that is the RF coil, RF generator, and the frequency at which it operates, the plasma to mass spectrometer interferences, which consist of the ions, cones, that is, you have the sample cones and the skimmer cones, and of course the ion optics, which defines what ions had to be separated or filtered out to be properly presented to the detector for measurements. So it could be either a quadrupole based system or a magnetic simultaneous system. And of course you have the mass analyzer, which is the detector, which could either be a completely digital detector or a semi-pulse analog detector. And the operating system, besides the computer and printer, you will also have to look at the vacuum, because the whole ion transmission happens in a vacuum mode to ensure it is free from all kind of external interferences and to have a kind of a ion separation from each other. So this gives you a kind of a purview. As you can see, the sample introduction to the ion source is similar to what you seen in ICP-OES that was earlier presented, but from ion sampling ICP interface, that's where the instrument differs, because you are going to suck in the ions, filter them in the mass analyzer to be presented to the ion detector. You have in this ion sampling ICP interfaces, you have a basic rotary vacuum pump, which brings from a normal ambient atmospheric pressure to 10 raised to -3 to -2. And then you have a turbomolecular pump, which further pushes it down to 10 raised to -5 to -6 torr. So this is a total kind of overview and schematic of an ICPMS. Let's take the first component, sample introduction system. Normally one looks with a 4-channel peristaltic pump. The sample introduction kit comes with an aqueous kit. You can also be offered with an HF kit if you have samples which addresses solutions prepared in HF, if you have geological samples, or high TDS samples, that is from seawater, if you have to do analysis of your selenium, mercury, arsenic, or if you want to do higher TDS samples, then you get a special kind of a spray chamber which dilutes the high TDS levels, decreases the content of the nebulized aerosol, and introduce them into the plasma. You have organic kit, which addresses your requirement for petroleum samples and volatile samples like naphtha. Just to add more over here, please note that an ICP-MS is all about trace and trace analysis. We cannot just push in an ICP OES measuring range requirement into an ICP-MS, because the factor of dilution will bring about a major error in your reporting format. So let us understand the different parameters after the plasma is ionized. You have the cones, which is the first line of the mass spectrometer. You have the sample cone of 0.8 mm orifice, which picks up the core of the plasma, and then you have the skimmer cone, which then sucks in the basic internal core of the ions, which enters between the sample and the skimmer cone. This zone is kept at a cooler temperature and under vacuum, causing the ions beam to expand, and you are able to suck in the best part of the core ion beam. These cones can either be offered in a nickel material or a platinum material. The platinum material addresses high TDS application. It also addresses your HF application. So these are the two parameters which is looked into the plasma ion interfaces. Once it enters there, then you have the quadrupole system. The quadrupole system works as a mass filter. You have 4 rods present in a cross-functional position, It has a combination of RF and DC voltages. They are alternatively used to filter out only a particular mass to the detector, and it filters out the other isotopes. So this is basically a kind of a sequential ion optic measurements. There are certain rules that is associated with the quadruple ICP-MS. Number one, to address certain interferences, you have to lower or power down the plasma levels at 650 to 950 watts so that you can address mass of the elements up to 50. If you have mass above 80, they cannot be still filtered out. Then you use a coalition gas where helium is used as the preferred gas. This helium gas collides with the species which mimics the analyte species, and you can further filter them to be measured. The reaction gas works for mass above 80 because the collision no more functions better for mass above 80. There you can use a combination of hydrogen or ammonia or oxygen or methane, but hydrogen is preferred because of its corrosive effect. It is more better to use with hydrogen. These are some of the drawbacks one use with a different kind of reactive gases like ammonia, where you can address the interferences on arsenic, selenium, and chlorine. But in the process of filtering out the unwanted species which mimics arsenic, selenium, and chlorine, it combines with other isotopes like copper, zinc, titanium, and sulfur if it is present there and forms cluster. And it is also known to stick to parts of the optics of the collision cell. The same thing, methane and oxygen. It is effective for a particular element, but it is ineffective if these other elements are also present. Then you have to completely flush it out and start analysis for fresh for these other elements. Additional rules of the quadruple ICP-MS is the kinetic energy, which is associated when you do the collision measurements. When you have helium as a preferred gas for colliding with the interferent species, it also collides with analyte species. During this process, the species generates a kinetic energy and it travels a distance. But this distance is a very short distance because post-kinetic energy effect, we differentiate the analyte species from the polyatomic species by building a kinetic energy wall. The polyatomic species, after if it is struck by the colliding gas helium, it cannot travel further and its charge is minimized. So you build a kinetic energy wall and allow the analyte species to jump over this wall, whereas the polyatomic species are sucked down because it cannot jump over it. Second is the length of your optics of a collision reaction cell should be as short as possible because the kinetic energy associated with the analyte species will only be limited to a particular distance. After they are filtered, they are introduced into a detector. Now, in quadrupole, you use a single detector. The single detector receives the ions. The ions strike on the analog surface because it consists of two parts, the pulse and the analog. All these parts are diodes. So when it strikes on the given surface, a charge cloud is generated, which is multiplied as it's struck off each surface till you get a signal. If the signal is not significant, the threshold gate opens up to be measured in pulse, and that's where you want to do the trace analysis. Since it's a single ion detector, the pulse has to be changed, the analog measurements has to be changed, and that's where you will see on the left hand side on the x-axis different mass range peaks are measured because based on what elements has to be measured, the mass of interest is selected and the filter filters the particular ions to be introduced into the detector for measurement, and you have a peak hopping program in place to measure the different mass at different levels. And this is the reason why in quadruple ICP-MS there is a delay, because you measure only one isotope at a time. But if one sees in a simultaneous ICPMS, it cleans the total ion beam by discarding the neutrals, dirts, and photons. With the help of a curved flight path, the ion beams are directed and focused onto the mass spectrometer. The mass spectrometer measures all of them using a CMOS detector, right from lithium to uranium, and you have a collective measuring time of 60 seconds. This simultaneous isotope measurements throws up a lot of features. Number one, non-destructive mass spectrum. That means I do not lose any of the data. It records the complete mass spectrum. I can understand what are the unexpected interferences. And if you will see on the right hand side, this is a standard sample offered by Merck to protect and to identify the authenticity of the product. They dope it with a signature element, that is barium at 138, to show the customer this is an original solution coming from them. Second is you can review your samples wavelength spectrum or the mass spectrum after it is no longer available with you. And this is particularly important is when you have limited samples, precious samples, or samples which are not stable enough to last longer. Second advantage of looking into simultaneous detection is you can do your isotope ratio measurements of two different isotopes of a given element, not one after the other, and this eliminates the interferences generated from the flickering noise of the plasma or the pulsating vibration from the peristaltic pump. That includes even from the pulsation from the laser ablation also. Simultaneous ICPMS offers complete mass range measurements of different isotopes right from lithium to uranium, and it offers a very good standard deviations. Like if you will see, this table shoots off with lithium and ends up with lead. Application it addresses is basically rare earths, one of the core requirements in ICPMS because they are present, as the name suggests, are quite rare. So the detection limits are pretty lower and they are need to be properly identified, quantified. Similarly, your water detection limits, if you want to do very ultra pure water, specifically for the semiconductor industries, these are the levels which the instrument can support for the detection limits in water. Precious metals is also another important industry which looks at the purity of the metals by understanding the impurity of the elements present and giving a whole perspective about the purity of the metals, which has to be certified, stamped, and given to the customer. And of course, pharmaceuticals, to address the mercury levels, it has been an important parameter to look at ICPMS because the detection limits of mercury as per US P232 and 233 requires the need of an ICPMS, and this is where an ICPMS looks at it. With the help of additional accessories, one can also do further applications. With the help of HPLC, you can do your speciation studies for chrome 3, chrome 6, arsenic 3, and arsenic 5. Using ultrasonic nebulizer, one can push down the detection limits of solutions which contains very low TDS levels. Auto samplers and auto diluters improves your sample preparation, dilution factors, and try to minimize and avoid the marginal errors coming from dilution. Laser ablation system addresses solid sampling and specific spot sampling of your given samples, which is very much matrix dependent. So your standards you should also have to the matrix for which it is being analyzed. Some of the routine maintenance that is associated with ICPOES still continues with ICPMS. That starts with the sample introduction system, where you routinely check your nebulizer, your spray chamber cleaning, your torch cleaning, pump tubing elasticity. You routinely check your cones, clean them or rotate them to enhance the life of it. Ion optics comes part of your service contracts. They have to be understood what is the intensity count it generates. Your detector needs to be sensitized. It has to be topped up with using cross calibration standards, because most of the detectors are either pulse or digital or completely digital. If it's completely digital, you don't need the reuse of cross calibration standards, wherein the pulse mode or the analog mode is brought up to meet the digital mode. And of course, the vacuum pump, specifically if it is a rotary vacuum pump, the oil top up has to be done. Additional accessories what are required for an ICPMS is you need to have an AC room with double door and air shower curtain. A class 100 to a class 1000 room is one looking at. You need to have an acrylic enclosure for your auto sampler to ensure that we or the room should not be the source for contaminating the samples, because we are doing ultra trace analysis. Fume venting for the vacuum pump and the plasma. Suitable UPS to run the system with at least 30 minutes backup. Computer and printer to be provided. Argon gas, collision and reaction gas. This also has to be looked into. And the kind of sample handling management. All your samples should be contained in not in a quartz system, because quartz can leach, silicate can come out, it can add to your analysis. So mostly one can look at LDPE or HDPE or polypropylene or PTFE, popularly known as Teflon, or PFA kind of sample containers, pipettes. Some of the recurring consumables one look at in a quadruple ICPMS is plasma sheet or electrode for holding the cold plasma power. Multiples is specifically when you use corrosive gases, so the life of the octopoles or universal cells or Q cells, they come down drastically. Cone interface interchange, they have to be routinely monitored to be seen that they do not corrode or become saturated, wherein they entrain or entertain more of ions from the plasma. Detector life, cross calibration standards, normal standards, vacuum pump life, RF generator, optic maintenance. And if your ICPMS is not used for a long time, you need to give an optic gas back flush to ensure that atmospheric air does not enter along with the particles that I've presented. I'm open for questions to take it.
Thank you, sir.
Yep, thank you.
We have some questions. First question is, how can we analyze the metal nanoparticles and what parameters we can check?
For metal nanoparticles, first of all, we have to understand the standards that is available. Based on the standards, the calculation is fed, and once that is calibrated, we run a particular value of the nanoparticles into the samples to be measured and quantified. So first, we have to have matching standards of the given nanoparticle size. And different nanoparticle size, the isotopes vary according to their requirements. I can give more details if the email IDs are shared. We can address this. And what type of nanoparticles that needs to be measured in this, I would like to have more analysis, more information on this.
So second question, which accessories can be attached to ICPMS?
It depends on your requirement. If you're doing speciation studies, you can attach an HPLC or a gas chromatograph. If you're doing specific spot analysis, then you can attach a laser ablation system. You can also couple it with an electrothermal vaporizer if you want to vaporize powders of any metal samples which is having less than 3000 degrees centigrade. And of course, an auto sampler and auto diluter.
So next question, can we detect all the rare earth element by ICPMS?
Both ICPMS and ICPOES can be used to detect rare earths. It depends on what detection limits we are looking over here.
Okay. Thank you, sir.
Thank you very much.
Thank you. We have a next upcoming webinar on NMR, which will be held on 25th November. Registrations are now open and links are listed on our website. Thank you so much, Mr. Milind Pathare and Mr. Anthony Thomas, for giving us your valuable time and delivering us a talk. A special thanks to Professor Anil Kotantrial for initiating a webinar series on instrument placed in our SAF IIT Bombay. Thank you, Dr. Gajendra Saini, for all your support. Thank you, Ms. Vinita Anvekar, for all your support. Thank you, our IT team, Mrs. Nidhi Goel and Mr. Jagdeep Singh, for all your technical support. Thank you all the participants for making this event successful. Stay safe, stay healthy. Thank you. Have a
Thank you,
nice day.
Rishma. Thank you
Thank
to
you.
Safe Team and stay safe.